everyone, today I'm starting chapter 26 for matrices. The last page of your chapter in your summary book outlines the learning intentions and objectives for matrices, the entire module. So for chapter 26, we want to be able to define and understand matrix representations, use them in real life, know how to use them on the calculator, and to apply the conditions relating multiplication of matrices. So chapter 27, a little bit more application type, so we're looking at identity matrices and inverses, being able to calculate the determinant and so on. That's to help us to pretty much be able to solve for matrices. And we're going to apply these to real life situations, and we're also going to look at transition matrices and make predictions using transition matrices, and obviously relate them to real life. So once again, it's quite a worded module, but hopefully the content won't be very difficult. So for today's learning intentions, I'm going to go through exercises 11A and 11B. So we want to learn and understand what a matrix is and how it can represent information. We want to understand the properties of a matrix and also how to use a matrix to represent information. Okay, so a matrix is used to represent information. So for example, here we have showroom 1 and showroom 2, and each of them have a set of information for Ford, Holden and Honda. Sales in a particular month can be represented by a 2x3 array of numbers. So think of this like a table. So over here we've got rows for each of the showroom, and each of the columns represent a different car. So if we think about this matrix, a matrix is a rectangular array of numbers, and it's set out into rows and into columns. The numbers in the array are called entries or elements, so each one of these, so 10 is an element, 15 is another element. Matrices are usually denoted by capital letters A, B, and C. So when I turn this into a matrix into a second, I'm going to call this perhaps matrix A. And finally, the size or the dimension of a matrix describes the number of rows and number of columns. This is called the order of the phoenix. Oh wait, it's called the order of the matrix, sorry. So the order of a matrix is the row times the columns. So in this case over here, it has 2 rows, so 1, 2, and it has 3 columns. So that's why we would say this matrix here is called a 2x3 matrix. So this is the information. Let's try and set this out into an actual matrix. All we have to do is we have rectangular brackets on either side, and we can just write our entries in like this. And there we have our matrix. We need to label it. Let's call this matrix A, and that's it. That's your information represented. Example 1 in your book is to be able to label what the order of these are. So let's look at matrix A. Matrix A has 2 rows. So here's our first row, here's our second. So that's a 2 by. And then matrix A also has 3 columns because that's 1, 2, 3. So the order of this matrix is a 2x3. In general, the formula for the order is the rows by the columns. Please don't get these confused. If you write columns by rows, it will be incorrect. So make sure that you know your rows from your columns. For this one, we've got 1 row, so that's a 1 by, and we've got 3 columns. So that's 1, 2, and 3. So that's going to be a 1x3 matrix. Okay, so you need to also know a few specific words of matrices. So these are special matrices. A row matrix has only 1 row, so the order of this particular matrix is a 1x3. For a row matrix, you'll always have that number 1 there, so in general, it's a 1 by whatever the column is. A column matrix has only 1 column, so that's, in this case, it's a 2x1. Same idea, it's going to be row times 1, because our column will always be 1. A square matrix has the same number of rows as columns, so its order is m times m, so as in the number's always going to be the same. A square matrix can be anything from a 2x2, 3x3, a billion by a billion. It doesn't matter as long as the numbers are exactly the same. Okay, another type of special matrix is the transpose, which we label T of a matrix. So the transpose matrix, all that it does is that it transposes the matrix by changing all of the rows into the columns and then all the columns into the rows. So if we have a look at this matrix over here, we can see that this first column over here, 1, 3, 5, has become the first row. In the same way, the second column has become the second row. You can also think of it in terms of rows to column. So this first row has become my first column. And so that'll switch it for you when you do your transpose matrix. When you do a column matrix and transpose that, that'll become a row matrix. To do this on the calculator, what you want to do is type in a matrix. So to type in a matrix, we're going to press this button over here. There's a few different options of typing matrices. So this will give you a 2x2. This will give you a row matrix, a column matrix, and this one will give you any size that you'd like. So if you click on it, I could perhaps want the number of rows to be 3 and the number of columns to be 2. Type in whatever you'd like. And then to transpose that, what we'll go to is menu, matrix and vector, and transpose. So that'll put like a little T there, and then you press enter and it's transposed it for you. So as you can see, the first column, 146, has become the first row, 146. Okay, Diagonal matrices are another type of special matrix. So a leading diagonal is that diagonal there that goes from left to right, top to bottom. And the leading diagonal has particular numbers, but every other element is a 0. So that is what we would call a diagonal matrix. An identity matrix is a special type of diagonal matrix in which the leading diagonal is all 1s. These only occur in square matrices. So the 2 by 2 identity matrix has 1s down the diagonal like that. 3 by 3 in the same way has 3 1s instead of 2. Okay, some more special matrices that you need to remember. The next one is a symmetric matrix. So that is a square matrix that is unchanged by transposition. So if you try to switch the rows and the columns, there won't be any difference. You can also think of it, if I were to draw a line down my diagonal, as you can see, it looks exactly the same. It's symmetrical. So your 4 and your 4 is there, 5 and 5, 6 and 6. So this is what we would call a symmetrical matrix. A triangular matrix, there are 2 of them. An upper triangle one is where I have a leading diagonal, and then a triangle is formed in my upper section of it. A lower triangle, same thing, I have a leading triangle and then I have a lower triangle that exists within it. And that's the end of those special matrices. So let's try an example. This is example 2 in your notes. So types of matrices. Consider the following square matrices, write down all of these. So the first one is the upper triangle. So what we're looking for is a matrix that has a leading diagonal and then has 0s everywhere else and has a triangle in the upper part of it. So looking at these ones, that looks like this option over here. Here's our leading triangle. Got 0 in all of our other elements, and then our upper triangle exists there. So let's label these. That's 1, 2, 3, 4. So this is going to be 2. The identity matrix, so we're looking for a matrix that has 1s down the diagonal and 0 everywhere else. That looks like option 1. Diagonal matrix, so we have numbers down the leading triangle, like leading diagonal, and 0s everywhere else. So that looks like that's option 3. And the symmetric matrix, where we have a leading diagonal, and then all of the numbers across are exactly the same. So that looks like option 4 over there. Okay, so to finish this exercise off, we're now going to look at specific notation for a matrix. Every element is called a certain thing. So if this is matrix A, then every element is going to be called A, and then depending on its row and column is going to be called a number. So the way that we always label it is we have our matrix, and then we have our row number. So in this case, this element here is row 2, so that's row 2, and it is column 3. And so this will be called A23. Please note that sometimes they don't actually write the comma and they might just call it 23. So this number isn't 23, it's still A23. So you just need to know which element represents what. So for example 2, for the matrices A and B, write down the values of. So the first one we're looking for is A12. So that means we're looking for row 1, column 2. Well, here's row 1 and here's column 2. So when we find the intersection of that, that's 5. For part 2, I'll do this one in a different colour. So now we're looking for row 2, column 1. So here's row 2 and here's column 1. So the number we're looking at is -1. For A33, we'll go another colour again. Here's row 3, here's column 3. So the number we're looking at is 6. For B31, we're looking at row 3, and we're looking at column 1. So the number we're looking at is 1. I hope that's pretty straightforward. We need to learn how to use notation to be able to apply it to these types of problems. So constructing a matrix given a rule for the ijth term. So this can be kind of tricky, but hopefully it's not going to be too hard once you get around it. So they're giving us some statements, and now we have to try and fill it in. A is a 2 by 2 matrix. So let's start off by drawing up this matrix. So that's A, and so it has 2 rows. Let's split it up into rows and 2 columns. Okay, so this is going to be element A11, element A12, A21, and A22. Now I can put commas there if you'd like as well. Okay, so the element in row I and column J is given by this rule, construct the matrix. So what that's telling me is that element A11 is equal to I plus J. So in this case, I, so that's the number of rows, is 1, and J, which is the number of columns, is 1. So what it's telling me is that the element is going to be 1 plus 1, which is 2. So this element over here, if I write that in, is 2. Same idea here. So this is going to be I plus J. So 1 plus 2 is 3. I plus J, 2 plus 1 is 3. And I plus J, 2 plus 2 is 4. I hope that makes sense. There's a couple of questions in your exercise that you can practice on this. To finish this off, so that was the end of 11A. This is 11B, but I just thought I'd include it because it's a pretty short exercise. We're now going to convert worded problems to a matrix form. So example 4 says, convert the 16-digit credit card number into a 2x8 matrix. List the digits in pairs, one under the other. So this is a key here, one under the other, to know exactly how we're going to write it. Now it's a 2x8, which means I have 2 rows, 1, 2, and I'm going to have 8 columns, so 1, 2, and so on and so on. So when we write our matrix, we don't really usually write those numbers in, and we can call it maybe C because of credit card. So we want to list the digits in pairs. So get them in pairs. So 4 and 0, that's a pair, and one under the other. So that's 4, 0. Then the next pair is 4, 5, 3, 0, 5, 7, 2, 3, 5, 6, 0, 9, 8, 7. And I hope you've gotten the hang of that. Now, I obviously made my matrix a little bit too big, so what you can do is grab your eraser and rub that bit out. Okay, and that is how you would construct a matrix of that form. Example 5. Now, this is a tricky one over here. Well, it's not tricky, but it's maybe a concept that you haven't seen before, in which we have a network or a diagram, and we're going to represent this information into a matrix. The first thing that we want to note is that there are 5 possibilities. There are 5 towns, there are 5 whatever it is. In this case, they're towns. So what we're looking for is the relationship between each of these 5 towns. Now, whenever you're converting these types of problems, you're always going to have a square matrix. And it's in this case, it's going to be a 5 by 5. And I made my matrix too big again. Okay, and what we're looking at is the connection between each town to another. So if it is joined, then it's a 1, and if it's not joined, it's a 0. And so what we're doing is generate a matrix to show the number of country roads. So if something has more than one country road, then we will count each of those. So let's start off. Country road 1, to go to country road 1, there is no pathway. There's no way you can go from 1 to 1. So that would be a 0. To go from 1 to 2, there is one road. So that's this road over here. That's 1 to 2, and so that means I can also label 1 to 2 over here as one road. To go from 1 to 3, there is no pathway. There's nothing that's connecting it. So 1 to 3 is 0, and same over here. 3 to 1 is 0. 1 to 4, there's another road there, so that's a 1 and a 1. And then finally from 1 to 5, there is no direct path. So what we're looking at is the direct paths. There are no direct paths. Now I've drawn this matrix kind of badly. Obviously you wouldn't do what I'm doing and draw it outside of the matrix, but I've just run out of a little bit of space. So I'm trying to make this a little bit better. Okay, and then we're going to go through each of them and do that. So 2 to 2, there is a path because there's a loop there. So 2 to 2 is 1. 2 to 3 is 0. And then we can also fill it down here. So 2 to 3 is also 0, or 3 to 2. 2 to 4, well, there's one path. And so one path there. 2 to 5, there is one path to go to 5. So that's 1 there and 1 there. All right, 3 doesn't actually go anywhere. So I can just go ahead and fill in zeros there because 3 isn't connected to anything. You can check 1 by 1, but that's probably the easiest way to go about it. Okay, from 4 to 4, there are no paths from 4 to 4. However, from 4 to 5, there are 3 different paths. And in the same way, from 5 to 4, there are also 3 different paths. And so the last one that's left over is 5 to 5, and there is no path in between it. And there you have it. That is your matrix. Once again, you can fix up your bracket to make it look a little bit better than the one that I just drew. But that is pretty much how you use a network to be able to construct a matrix. Alrighty, so to finish off, I'm just going to revisit the learning intentions. So we wanted to understand what a matrix is and how we can represent information. So being able to convert all these worded problems to matrices. To understand the properties, so we know the rows by columns and the order and all the special types, and know how to use a matrix to represent information, which is what we did in the last bit. So I hope that's all made sense, and I'll see you next time.